to one of the InterQ workshops now hosted by Promicron partner and in the InterQ project. Maybe you have heard of Rainer and me, or maybe we met before. I just checked the names. Some of them are well known. And yeah, happy to have this workshop with you, or this kind of presentation. What is the topic? What is the content I would like to share with you? We talk about digital machining with Spike. I have some use cases, or I would like to discuss use cases. I would like to explain you the functionality and the strategic potential more in detail to you. Use cases are pretty clear. We already have 3 in the InterQ project, but yeah, so my main focus relies on the functionality and the strategic potential, combined with a short summary about the current first results of Promicron contribution in the InterQ project. Yeah, as agenda, I will start with the following topic. What does Promicron understand by digital machining? What is our goal? What is our uniqueness, or what do we want to achieve? Then I will explain the unique measuring concept. I will explain the current situation where we are currently with the software and with the hardware. I will give you an outlook for the development. Then we will go quickly into the use cases of InterQ, and at the end we will have questions, and we have the time for discussion. I will start my timer. 40 minutes. In 40 minutes, I would like to discuss the questions. To start with the questions. If there are concrete questions in between, please let me know. I can say if this is relevant now or if I will answer that later on. But sometimes, yeah, direct questions on specific topics need to be answered directly. What is it all about with Spike? This is a little bit the pitch I use also in sales, and I start with a question. How we achieve cost reduction for single batch size and serial production. And to introduce the topic where we are focusing on, I start with another question, and it says, what do these products have in common? They represent a little bit the industries. It's the aerospace industry, die and mold, automotive industry, high precision machining, and the answer is they all need perfect surface quality and form and position tolerances. And it doesn't matter if it's a Blisk or a blade or a die or a huge precision workpiece, or if we talk about micro machining. To avoid systematic and sporadic errors like this, for example, a chatter mark or chattering or a scrapped thread, or single cutting edge tool wear and single cutting edge breakage, here with a full fluted end mill, here with a ball end mill. So it's a systematic error here with systematic tool wear, and here it's a sporadic tool wear with a scratch on it with a chip. Here we see a micro chip tool wear on a reamer, which cannot be seen by with your own eyes, but this leads to a bad surface quality of the hole. But we also have sporadic mistakes like a tool deflection if when the form and position tolerances are not in line, and yeah, micro machining, tool breakage, but even quality issues are also a topic. And at least, last but not least, issues like a 10 micron chip between the tool holder and the spindle, or a spindle overload, or while cutting, or if the clamping force of the tool holder is not enough anymore. All these systematic and sporadic mistakes happen in machining, and in order to avoid these, the manufacturer needs to check every workpiece made. So he has downstream quality check efforts. And depending on the customer, they every 10th or every, I don't know, or they only check it at the functional test. So that means downstream quality effort, which means costs, documentation effort, and time. And I think this is also the main topic of InterQ. We want to have the in-process quality control. We want to be more competitive by cost reduction, by making the production more simple, and to get costs and efforts and costs which we have pre-process and post-process, we want to have in process. So my main question to the end users is, how much does your quality cost you? Because this is what we want to reduce. How do we, this is an overview about our Spike solutions per user need. Some of them, if we look in from the pre-process analysis and optimization, we can use the collected data, the system as a diagnosis system. When we talk about downstream use of the generated data, we are in the area of quality control. And if we are in line, in process, then we have process monitoring features to detect errors and automatically react. So basically, these are our three user groups. When we look at the goal of cost reduction by in-process data, this graph should give you a little bit the overview how we see the things and where we see us Promicron located. Here we have the value chain of a production site. In the beginning, we have the construction with a 3D or with a technical drawing. In pre-work preparation, we have systems like VariCut Force, or we have the CAM program from Solid CAM or from other suppliers. In production, when we look at the machine, we have the machine itself, we have the machine data, we have external sensor data. When we look at the tool, there is a tool manufacturer with the tool management systems. When we look at the quality, there are the quality measuring systems all downstream, or a bloom laser, which can be used from process to process, but on the milling machine. And when we look at the process itself, then we also have data from our Spike technology. So there is our sensor and located. Our data generation method, but the software from Promicron, the tool control center, is like an overlapping approach in order to, based on the data that we collect, we want to provide output for every different user group along the value chain. For the goal to bring the downstream quality inspection effort in production and to have an exchange between the pre-work preparation and the production, for example, to get a reference force value in single part production from a CAM program or from a system like VariCut Force or something like this, and to monitor then this value in this information, this force level, and to also give feedback to the CAM program where to optimize this the program. Next point of the agenda, the unique measuring concept. Is there any question until now? Already coming up for that kind of introduction. It seems not. Let's jump into the next topic, the unique measuring concept. Spike is not only a sensor where we started with. Spike has also, when we talk about Spike, we need to talk about the measuring concepts, the uniqueness, which kind of signals we provide. Spike is also a software, And the topic of use cases is also something I would like to explain quickly. Which kind of sensors do we have? Basically everything what is on the machine, because now we have a option to read the machine information, for example, the spindle load, but the access data, the NC code, the tool table, and all these information, we also see that as sensor or as signal. And next to that already existing information, Promicron is now adding sensor data force signals directly from the tool holder as a retrofit solution, or the in-spindle integrated solution designed by DMG Mori Group and spindle manufacturers. What's the uniqueness? We do not only measure the feed force and the torque, which can be also read by the axis load or the spindle current. In our case, we measure it directly. No, we also have now the bending load, the radial forces acting at the tool. From two directions, we look from the tool perspective, not from component perspective. And because of this, we are able to visualize the forces on each cutting edge, or we are able to, or we have a signal, the bending moment signal, which is a signal that correlates pretty much with the quality. So here we have a pretty nice and fancy quality related signal. The signal is measured directly and transferred wirelessly to a receiver, which can be connected with the machine or not in order to be flexible. But here it's the concept is wireless. The software. Software is, we started with a normal diagnosis software. Now we designed a new software approach, being able to store the data web-based in a database. That's the first feature. The second is we have access now to not only our own sensor signals, we can also read the machine signals, which I said, so data acquisition has been improved. It is inline, so we can record data automatically via the PLC or via the NC code, for example. And the software is getting more and more monitoring or analysis features. And as you know, a software can improve by software modules or add-on modules. We just basically started with a new concept. Use cases. Use cases is a very interesting topic. As we have it in the InterQ project, we try to involve the partners or the companies along the value chain, because we know we cannot solve all the problems by ourselves. We are just part of the cake, let's say. As we see, it's pretty innovative, and yeah, we are actively working together on solving use cases together. And I think with our kind of sensor signal and the software tools which we provide, innovative approaches, business approaches, like which we also face in InterQ, are even possible. Let's go a little bit more in detail into the uniqueness of the measuring concept. Again, our strain gauges with the electronical components and with batteries sit on the holder in this ring or in the spindle. And because of this, we are looking from the tool perspective. We have the action force, the torque, the bending moment. And if we have a finishing operation like this, you see in this case, the single cutting edge is acting now in the material. That's why the load, the bending load, also has the time to jump back to zero before the next cutting edge comes in. But by looking at a time frame, it enables us to visualize the forces on each cutting edge. Why is that beneficial? Because if we have a tool wear problem, which leads to bad surface quality, and when we do not want to stop the machine, open the door, look at the tool, or look at the surface quality, we need another method. And as you know, force is a very good feedback out of the performance of the tool and the process stability. And this is what we do. We visualize the forces on its cutting edge with the patented Spike Polar software feature. And you see here the flower, let's say, or the cross is small and symmetric. And when the tool is wearing out, the force impacts, the angles are changing, the force value is getting bigger. And effects like a tool breakage or cutting edge breakage can even be detected because, as you know, as an engineer, you can read the picture. It's now unsymmetric and one force flower, let's say, has been lost. The problem is we can visualize, we can measure and visualize it, but how to monitor it? And here we are working on KPIs, process-specific values between 0 and 100 to give us a feedback about the condition of the tool. And if we have this in our software, we just need a machine reaction, a method for integration to achieve automation. How does that look in drilling? In drilling, we want to achieve quality-related issues like drill runout, centering errors, tool wear, chipping, or concentricity errors, but also topics like tool breakage are interesting. But as you know, sometimes the spindle load is even sensitive enough to detect if the process happened, yes or no. We want to focus a little bit more on the quality. And this is what we had here. We machined 20 holes and we were looking at the quality at the drill exit, and we found out that the tolerances of hole 11, 14, 16, 20 was out of line. That means the tool must have been deflecting. Can you see this in the feed force in the torque, which can be compared to the spindle or machine information? No, you cannot detect it. But let's have a look at the bending moment signal. And here we detect higher load at hole number 11, 14, 16, and 20. If we have algorithms like envelope curves or the KPIs, this could be interpreted, monitored, and with a machine reaction, we could even say this drilling hole or now the drill is not performing anymore, automatic tool change. So the concept is we are collecting big data directly from the sensor, but the software is filtering the data, and still we are able, by reducing the volume, and still we are able to use algorithms like the symmetry, like a chatter KPI, like a donut form KPI in drilling, or a runout KPI. Now, what's the current situation and the outlook for the development? How about, we thought in the last years, we thought about, now we have the external sensor data from Spike, but what about matching that kind of process related data with also existing data which is on the machine, like the machine data, access data, NC code, and the tool ID? I think we can generate much more benefits on that. And even when we talk about the topics digital twin and so on, everyone says we have a digital twin of the CAM program, of the machine, or even of the CMM part. But what about the process? And this is also found, also used in the InterQ project. And here we place the first version of our software, where we are now basically visualizing and matching the forces collected by the machine, spindle torque, or external sensors like the spike bending moment signal with the NC code and with the position, with the XYZ position of the tool, so the tool center point. And based on this, we do not only have a tracking software and a visualization, we can also export the data, and more features in the software like offset detections and so on will be available in the next years. This is the Blisk machining example, which we have shown also during the InterQ general meeting. I would like to show you now our typical Blisk example, which we have machined just 2 weeks ago when a machine tool builder was visiting Promicron. And my question to you is, can you find the error? Can you find the quality related issue on that part? The customer and the user, the visitor said, yes, I found something. It's here top on the left. And I said, okay, I didn't know what the data was giving us from the Spike software. So we started with looking at the spindle current. So the torsion signal from the spindle and in our Spike map software. And this is what we got. The force data with different force levels, colored in different values, linked to the NC code and linked to the position on the part. But yeah, it's like a big cloud. I cannot see any force differences. Then I just switched in the software to the torsion signal from the Spike mobile holder, which we have used, and we already saw a little bit more difference between the noise and the forces. And the coloring was already, also the scale was already coloring us it a little bit more in detail, but still I would say I cannot see the error. Let's have a look at the bending moment signal, which we collected, and now it is getting more clear. And this is exactly the same spot in the, let's say, in the digital twin of the process of the workpiece of the cutting forces linked to that spot of the part. So when we think about further production or line production, we have issues like chatter marks. With Spike, we can record that data. With Spike KPIs, we calculate, we analyze inline that kind of issue, and we create that output with the KPIs. If we have recorded now the first part, check the quality and see that this is good quality, then we, in a new software feature which we are working on, or which could be an option, we create a reference file. And now, if there is in the next part, if there is a chatter KPI warning, let's say, then we could mark it in the reference file directly where this is on the part, in order to know already in process if we have quality issues. So our vision is also fitting to the InterQ project and to the goals. The autonomous machining, continuous process adaptation, and 100% quality estimation without extra measuring effort needed is the main goal. The digital workpiece is the tool, I think, which enables us to achieve that. But until we achieve that level, a lot of homework needs to be done. Today and in projects, we are on the level of using the Spike technology as flexible diagnosis system. With the tool control center software, we are now having an inline data tracking opportunity. And in projects and in further projects like InterQ or other own projects which we are running, the error deviation or the error detection and advanced analytics is been done in order later on, or step by step, depending on the use case, to integrate that system directly also for monitoring and for automation. But these are all the homeworks on our roadmap, which we need to do together in order to achieve the digital workpiece. Now, I would like to go into the next topic, the use cases and the status of Spike technology in the InterQ project, if there are no questions until now. If there is a question, please just activate your microphone and let me know. Okay, none. I copied a little bit the slides from the last presentation from Xavier. Where are we in the InterQ project? As you know, there are 3 use cases from ITP, from Siemens Gamesa, and from Renault. In the grinding operations, we focused on now designing a more sensitive tool holder and to provide data here. And on this same side, we said if we have that data, we need to work on the algorithms and the KPIs and the data interpretation. So in grinding, our role is to provide a more sensitive holder and a more advanced knowledge about the error detection. And other features like the tool control center and the milling holders or drilling holders are used also in the other use cases. But here we are not really, we don't need to go in with new development since it's already available. So a quick overview about the physical sensor. Here you see the first prototype which we done. Basically, we are providing 2 solutions. One is with the standard sensor technology, but with an optimized and improved row holder a structure or design of the row holder itself to achieve a higher stiffness, but a higher sensitivity. And here we already received some improvements. We increased the sensitivity by factor 10, increased the stiffness by factor 2.5. But it's not enough. That's why we will provide a new sensor technology on that improved row holder design in order to achieve a much higher signal and sensitivity. The grinding wheel toolware was the second topic. We have here now already a little bit we collected with Xavier and his team more data on grinding, which is now being analyzed in order to find out if there are criteria which are quality related and which could be put in as with a spike KPI. This is something, a quick overview of some toolware trials which we have done. You see the Spike Polar. It is centered pretty good in the beginning. So this is the first output which we can get. The balancing of the grinding wheel is pretty good. But when we see the roundness of the Spike Polar ring, it's getting worse, especially in this area, and the force level is increasing because of tool wear. So these are now raw data signals which we are looking at more in detail. These are some other examples. Unbalanced effects or brushing effects, or let's say dressing effects, are now going to be investigated. I just wanted to explain here what we did. We have 4 different situations in the topper brushing example where we did a mechanical and an automated brushing process of the grinding wheel in 4 different situations, and this is the output, the force signal output, what you get after these situations. So if these are technical cases and process errors, they could look like this, and now we just need KPIs to analyze and monitor them. In the InterQ project, there's one use case from ITP where a lot of turning, but milling, but also drilling applications are in these operations. And what did we do here? With the CFAA, we installed the first version of the tool control center software, and we were trying to find out the sensitivities which are required and the software output which we are generating. And we used here a milling operation in this Blisk part, which we will now investigate more on with ITP itself. As outlook, what I understood that we want to go on, and also the CFAA team said that they are planning to get this reference InterQ project part also on one of these machines. And sure, we want to use our Spike map software on it for data tracking, not only the Spike mobile data, bending moment, torque, and axial force, but also the torque signal in order to find out in which operations do we get which kind of output and how do quality issues look like in that kind of data. There's the Siemens Gamesa use case. Here we are focusing more on grinding, where also the grinding holder, which is currently at IDECO for the testings, is being used. Here the grinding holder which we are developing is the main focus. But sure, reading the machine information, synchronizing it together in the tool control center software in the Spike map is a use case, but where we are not, we can use it, but it's not the main focus. And in the Renault case, I know, or I think you all know the backgrounds. Here we are focused a little bit more on drilling and reaming operations. I just wanted to emphasize here again, we did a similar application with a market partner or another company, a similar company like Renault before, where we found out that the bending moment is a pretty nice signal which could help to detect like single cutting edge issues or run out issues, form and position tolerance issues, and which can be used here as well. Yeah, I'm already reaching the end of the key fact information, and now I would like to go into a further questioning and discussion if needed. Since I know that many of you are from looking at the InterQ project from different orientations, I can help here to link the connections. Thank you very much for for joining that workshop, and let's now get more into the questioning and discussion.